This is Lab 11 on Rutherford Scattering. My name is Bridget Savitsky. Problem is that if an alpha particle is shot at gold foil, it should pass right through if the foil is low density and positive with electrons spread evenly throughout, but it's actually deflected or bounces right back. We can conclude from this that atoms have positive nuclei that are concentrated in a very small volume. The models used include the momentum principle and the energy principle. It's also important to note that a collision doesn't mean that they make actual contact, but that they've just interacted electrically. Here's a diagram of the experiment. An alpha particle is shot at the gold foil a certain distance y above the nucleus in the foil, and this is identified as the impact parameter b, and it's deflected at an angle theta. Looking at the code, I set the initial conditions of the x and y position of the alpha particle right here, and the nucleus is the origin. Delta t must be very small because of the microscopic scale of the experiment. I initiated the plots here and identified the mass and the charge of the gold and alpha particles, gave the alpha particle a certain speed in the x direction, and calculated the alpha's kinetic energy here. The impact parameter b is also the y position of the alpha particle. This red box calculates the net force, which is the electric force here. Then the momentum principle is used to update the momentum and then position of the alpha particle. This line of code shows that there's an equal and opposite reaction from the collision of the alpha with the nucleus, and then the nucleus's position is updated. We have both potential and kinetic energy, and the kinetic energy is the sum of the alphas and the golds. These lines calculate the kinetic energy of the alpha particle in mega electron volts. Finally, the scattering angle is computed. So the alpha is shot, it encounters the electric field, and then it's deflected at some angle, and the gold nucleus also moves slightly. Looking at the graph, the green is potential, the red is the kinetic energy of the alpha particle, the yellow is the kinetic of the gold, and then the blue is the total energy K plus U. Blue is constant because of conservation of energy, and it's also positive, so the system is unbound. This is where the collision of the particles occurs. Potential becomes positive, and kinetic energy decreases by the same amount, which is conservation of energy, but then suddenly repulsion kicks in, and the alpha's energy goes back to kinetic energy, and as it goes off, the potential energy decreases. We can also notice that the gold's energy increases then remains constant after the collision because no other force is acting on it. What if I was to change the impact parameter? I'll make it so that it's close to head-on. The alpha scattering angle is significantly increased, as did the energies involved in the collision. You can see what a strong impact changing the impact parameter has. By changing just one order of magnitude, we go from 77 degrees all the way to about 166 degrees. The plum pudding model doesn't work because if the nucleus's mass was over a larger area than it actually is, by the 1 over r squared law, the force should be much weaker, and the alpha particle should pass right on through, but it actually scatters. The collision is elastic because there's no change in the internal energies of the particles. The only significant changes we see are in the kinetic energies of the particles, as seen from the plot. In calculating the electric potential, it's easy to see why kinetic energy is the only significant change in the energy that occurs. If we take the initial separation, in this case, to be a very small number, say the diameter of an atom, we find that it's only a very small percentage of the kinetic energy of the alpha particle, which we can see right here. We can conclude that the scattering angle decreases as B increases because the collision is less direct. In reality, because the nucleus is so small, the alpha particle will miss it by a large distance, so the smaller scattering angles are more common. Ultimately, this angle enables us to see the effective size of the nucleus by observing the force it has. So what if the kinetic energy was significantly increased? The electromagnetic force is the net force, but if the alpha particle has a high enough energy, it can overcome the electric repulsion and make physical contact with the nucleus. That's when the strong force will come into play, where it will depart from the Rutherford formula. Just for fun, when I give the alpha particle a very high initial kinetic energy, so 7.6 times 10 to the 7th, you notice that even though the impact parameter is the same, the scattering angle is significantly reduced to 11.11 degrees because it can overcome much of the electric force that the nucleus gives. As a result of this experiment, the model of the atom significantly changed. This is the plum pudding model, and this is the modern model with an electron cloud and an extremely small concentrated positive nucleus.